In this problem, you can see that there is a sphere, solid sphere of mass m, which is placed on a rough inclined plane of inclination alpha, and this sphere, this friction is sufficient enough to prevent any sliding, and this sphere is being wounded with 3 turns of a wire which is carrying a current I. The radius of the sphere is r, and there is a magnetic field which is acting on the sphere in the vertically upward direction. So this sphere will not slide, as we have already discussed that the friction is sufficient to prevent any sliding, and the magnetic moment of this sphere will be like that, if you will see by Fleming's right hand screw rule. And the magnetic torque acting on the sphere will be in this sense, in anti-clockwise sense, and therefore it will balance the torque of mg sine theta. So let us first of all draw the FBD. Let us see that the friction will be acting on the sphere in upward direction, mg sine theta will be acting on the sphere in this direction, mg cos alpha will be acting in this direction, and normal reaction will be acting in this direction, n. So we can see that the torque of for equilibrium, the torque of magnetic field B will be equal to torque of mg, and torque of mg, or torque of friction we can say, because the torque of friction and torque of mg will be same. And let us write down the torque about COM. So torque about COM will be of friction F into R, and we know that for equilibrium F is equal to mg sine alpha. So this torque will be equal to mgr sine alpha, and it will be equal to torque of magnetic field. Now you can see, let us see the situation that M is like that. Let us draw the diagram on the next page. Because you can see that M magnetic moment is like that, and magnetic field is like that, and this is the inclined plane, this angle is alpha, and this angle is alpha, this is again alpha. So the torque of magnetic field will be mb sine alpha, and the value of m will be nia. Now n is 3. You can see that it is clearly shown that there are 3 number of turns. So n is 3, I is I, and area of one turn will be pi r square, where r is the radius of the loop, b is the magnetic field. So torque of magnetic field tau B will be equal to 3I pi r square B sine alpha, and this torque will be equal to mgr sine alpha. So this torque will be equal to mgr sine alpha. So cancelling sine alpha with sine alpha, r with r, we have to find out the value of I. So I is equal to mg upon 3 pi rb. This is the value of required current to keep this sphere in equilibrium. Now let us move on the next question. In this problem, you can see that there is a wooden cubical block of mass m and side A. It is resting on a horizontal surface, and there is a wire carrying a current I, which is wrapped around this square, this cube, in form of a square of side A, and a magnetic field B is equal to B naught J cap is switched on in this region. We have to neglect the mass of the wire, and we have to find out that if this block is in equilibrium, then at what distance from x-axis is the normal reaction is acting on this block, and what is the maximum value of current in the square loop for which this block will not topple. So we can easily understand the situation. First of all, let us determine the direction of magnetic moment. So you can see that as if you will rotate your right hand fingers in the anti-clockwise direction along with the current in the loop, then you will observe that the magnetic moment of the loop is in upward direction, like that, M. And M cross B is the torque acting on the loop, which is like that, M cross B. So tau will be equal to M cross B, and the angle between tau and the angle between M and B is 90 degree. So if I write down just the magnitude of torque, then it would be MB sine 90, which is 1. Now this torque is trying to topple this wooden block like that in clockwise sense. So therefore normal reaction will shift away from the center of mass like that, and it would be acting at a distance, let's suppose x, from the center of mass. Now mg will be acting in the downward direction at the center of mass, and hence we can say that torque of mg about COM is 0. About COM is 0. So what we can say that the clockwise torque of the magnetic field is balanced by the anti-clockwise torque of the normal reaction to keep this block in equilibrium, as well as normal reaction is equal to mg in magnitude because net force is also 0 on the wooden box, and we can equate mb to n into x. So m is nia, n is 1, I is I, area is a square, and b is the magnetic field. This n is the normal reaction, which is mg, n into x. So x will be equal to I a square b by mg. So this is the value of x from the x, where x is the distance of the normal reaction from the center of mass. But in this question we have to find out the distance of this normal reaction from the x-axis. So obviously from x-axis this distance would be equal to a by 2 plus x. Okay, so we can report the answer as a by 2 plus x. Now at what maximum value of current for which the block will not topple? You can easily understand the situation that as you will increase this current, this torque of magnetic moment and magnetic field will increase eventually, and it would try to topple this block in the clockwise sense. And till if we increase the value of current to a maximum value, then the normal reaction will be acting at the extreme point at this surface. Okay, so this will be the extreme shifting of the normal reaction, and after this point the normal reaction could not shift, and therefore at this point the current acting on the current flowing in this loop will be maximum, for which this block is not toppling. So we can find out the maximum value of current by just putting the value of x max as a by 2 from the center. Okay, so I max, this would be equal to I max a square b by mg. I max a square b by mg. So cancelling a with a, I max will be equal to mg by 2 divided by b into a. So this will be the maximum current that would be flowing in this loop, so that this box do not topple. Now we move on the next question. In this question you can see that there is a wooden disc of mass m and radius r, and it has a single loop of wire which is wrapped around its circumference. This disc is mounted on a massless rod of length d, and the ends of the rod are supported on these two hinges, A and B. Now this rod is horizontal initially, and it is keeping this disc vertically such that the plane of the disc is in vertical plane, and a magnetic field is acting on this disc in the upward direction B naught, and a current is set up in the disc like that in anticlockwise sense. So we have to find out the least value of current so that one of the support gets lifted off, which means that rod gets lifted off from one of the support. So first of all, let us find out the direction of magnetic moment. You can see that if this current is rotating like that, the magnetic moment would be acting in this direction like that. You can rotate the fingers of your right hand and you can find out the direction of magnetic moment. And as we can see that the magnetic field is in upward direction, the torque will be like that, m cross b. So this torque would be in anti-clockwise sense, and therefore the probability of the rod leaving the contact at point B is more. So to leave the contact at point B, we know that this normal reaction N, and this will be the mg of the disc. This N will be equal to mg. We are just assuming that the net force is 0 and the acceleration is 0 at the time of lift off, and obviously the torque which we can find out at this point. So torque about A. So torque about A is m cross B. I will tell you what I am saying. See, first of all, this torque is m cross B, and angle between m and B is 90 degree. So this torque will be mb sine 90 about A. And most of the students are having a confusion that m cross B is the torque about center of mass of the body. See, we have already studied the force couple in rigid body dynamics. You can go and check the playlist of the rigid body. And we have already studied in force couple that in force couple, the torque of the force couple, net torque of the force couple is same at all the points, and it is independent of the choice of the point about which we are finding out the torque. So this is also at force couple. You can refer to the derivation of m cross b, which we have done in the previous video. So m cross b was due to a couple forces acting in the different directions, and therefore we can refer it as force couple. And we know that the torque of the force couple is same about any point. So this torque m cross b can be written about A also, and the torque about A of mg is mg into d by 2. So we can say that m is n, which is 1, I into area is pi r square into b, and this will be equal to mg d by 2. So we have to find out the least value of current so that it gets lift off. So this current I will be equal to mg d by 2 and divided by pi r square b. So this will be the current required to lift off the rod from one end. Okay, now we move on the next question. In this question, you can see that there is a uniform ring which is carrying a current I as shown, and the mass of the ring is m and the radius of the ring is r. Now this ring is suspended by this point by two strings OA and OB, and there is a uniform magnetic field B naught in this direction parallel to the diameter of the ring AB. Now we have to find out the tension in these two strings. So first of all, let us write down the tension as T1 and this is T2. So we know that due to the magnetic moment which is in the upward direction, there will be a torque acting on the ring in anti-clockwise sense like that. So this tension T2 will be greater than T1, and we can say that T2 cos theta, which is the component of T2 in this direction, T2 cos theta, and this is T1 cos theta. So T2 cos theta will be balancing, will be plus T1 cos theta will be equal to mg of the ring. So we can say that T1 plus T2 is equal to mg by cos theta, and cos theta is obviously 60 degree, so T1 plus T2 will be equal to 2 mg, first equation. And the torque of T2 will be calculated at this point, center of mass. So torque of T2 will be T2 into this distance, and if this is theta, then this is also theta. So this distance will be equal to r cos theta. This is r, and this would be r cos theta. And obviously the torque of m cross b is in anti-clockwise sense, and therefore the opposing torque, which is balancing out this torque, will be in the clockwise sense. So the torque of T2 will be greater than the torque of T1. So we can write down the torque of T2 as T2 into r cos theta minus torque of T1 as T1 into r cos theta, and this net torque is equal to m cross b, which is mb sine 90 degree. So T2 minus T1 into cos theta is equal to m. Now we have already taken this r in the denominator, so m is I into pi r square, but we have cancelled that r, so m will be I into pi r into b, and cos theta is half, so T2 minus T1 will be equal to 2I pi rb. So if we add up these two equations, then we can say that T2 will be equal to mg plus I pi rb, and T1 will be equal to this is, we can substitute the value of T2 here, so T1 will be equal to T2 minus 2I pi rb. So T1 will be equal to mg minus I pi rb. So this will be equal to T1 and this will be T2. Now we move on the next question.